Hello friends, today I am going to talk on the famous Pythagorean theorem, Pythagoras theorem. So let me start with the theorem. For a right angle triangle with sides A, B and hypotenuse C, the area of the square on hypotenuse C is sum of the areas of the squares on B and A. A square plus B square equal to C squared. That's the theorem. The converse is true also. If for any triangle the square of the sides equals the sum of the squares of the other two sides, then the triangle is a right angle triangle. So the converse is also true. A brief history. There is a debate whether Pythagorean theorem was discovered once or many times in many places, and the date of the first discovery is uncertain, as is the date of the first proof. Historians of Mesopotamia mathematics have concluded that Pythagorean rule was in widespread use during the old Babylonian period, 20th to 16th century before Christ, over 1,000 years before Pythagoras was born. Still, we get the theorem in the name of Pythagoras. The theorem is named for the Greek philosopher Pythagoras, born around 570 BC. The theorem has been proved numerous times by many different methods, possibly the most for any mathematical theorem. The proofs are diverse, including both geometric proofs, algebraic proofs, with some dating back thousands of years. In India, Budhayana Shulva Sutra, the dates of which are given variously as between the 8th to 5th century BC, contains the list of Pythagorean triples and a statement of the Pythagorean theorem, both in the special case of the isosceles triangle and in the general case, as does the Apostamba Shulva Sutra 600 BC. So Indians have a contribution also in the Pythagorean theorem. So here is the easiest proof, as I found in the list. So if I take the triangle A, B, C, the right angle triangle, 4 copies of them, then the bigger square is the A plus B whole square, has the area A plus B whole square, whereas this white square has the area C square, and the areas of the triangles are half AB, so 4 times that. So A square plus B square plus 2AB equal to A plus B whole square. The area of the big square equal to 4 times half AB plus C square, which is 2AB plus C square. So we cancel 2AB on both sides and we get A square plus B square equal to C square. So that is the easiest proof. Einstein gave an interesting proof of by Pythagorean theorem. He drew from the right angle vertex, he drew a perpendicular on the hypotenuse, and the angles are alpha here, beta and beta here is easy to prove. Then we get sin alpha equal to A by C equal to cos alpha from this triangle, and sin beta equal to B by C equal to cos alpha from the big triangle and the small triangle. Then the length of the hypotenuse C equal to B sin beta plus A sin alpha, that is easy to see. And if we replace sin beta by B by C and sin alpha by A by C, we get the statement A square plus B square equal to C square. So that's Einstein's interesting proof. Pythagoras theorem with regular polygons. In place of the square, which is a regular foregone, if we use equilateral triangle or a regular pentagon or a regular hexagon or any regular polygon, the area of the polygon on the hypotenuse equals the sum of the areas of the polygons on the other two sides. So C equal to A plus B, and that is true for any regular polygon. Now, not only the regular polygon, if the shapes are of similar, if the shapes are similar, at least the angles are equal, then also we get the Pythagorean theorem, area C equal to area B plus area A. Now we go to Pythagorean triples. 3, 4, 5 is a Pythagorean triple because 3 square equal to 9 plus 4 square equal to 16, which equals 25, which is 5 square. So 3, 4, 5 is the smallest Pythagorean triples. Then we have 5, 12, 13, 7, 24, 25, 8, 15, 17, 9, 40, 41. These are all the Pythagorean triples below 50. Now we have Euclid's general formula for any three numbers k, m and n. M is of course bigger than n. If we take a equal to k into m square minus n square, b equal to k into 2mn and c equal to k into m square plus n square, then we get a square plus b square equal to c square, which is easy to prove. So for three numbers m, n, and k, the above formula generates all Pythagorean triples. So given any three numbers m and k, this formula gives a Pythagorean triples. Not only that, all the Pythagorean triples are of this form. Now, mathematicians tried to generalize it, and there came Fermat's last theorem. The French amateur mathematician Pierre Fermat around 1637 conjectured that Pythagorean triples do not exist for higher powers. So, a to the power n plus b to the power n equal to c to the power n doesn't have any integer solution for n greater than 2. That is Fermat's last theorem, and it was proved in 1995 by Sir Andrew Wiles, and that earned him Nobel Prize in 2016. So that's about Pythagorean triples. But surely we may not be able to generalize in the degree, but we can think of Pythagorean n tuples, m square, m1 square minus m2 square minus mn square plus twice mn m1 mk whole square k equal to 1 to n equals m1 square plus m2 square plus mn square whole square. Any primitive Pythagorean n triple a1 square plus a2 square plus a3 square plus an square equal to c square can be found out by taking m1, m2, mn as c plus a1, then a2, then a3, an. So that's the story of Pythagorean triples and Pythagorean n triples. I'll stop here. Thank you.